All right, today we're going to talk about the limit and direct comparison tests. And these two tests expand the variety of series you're able to test for convergence or divergence by allowing you to compare a series having complicated terms with a simpler series whose convergence or divergence is already known. And a simpler series is usually going to either be a p-series or a geometric series, because those are two types of series that we can just glance at and know, oh, I know that converges, or I know it diverges, depending upon what the p or the r value is. All right, so what the limit comparison test does is we're going to let a sub n be the given series, and we're going to let b sub n be the comparison series. And as long as all of your terms for a sub n and b sub n are positive, which they will be, and that's not really something that you have to worry about checking, then if the limit as n approaches infinity of that original series divided by the comparison series equals L, and if L is a finite and positive number, then either both series converge or they both diverge. All right, so I think the easiest thing is just to jump into an example and show this to you. So we're going to try to determine whether the sum of 1 over n plus 1 converges or diverges. Now, we could use the integral test to do that because we do know how to integrate 1 over x plus 1. We would use natural log to do that. But like Daniel said a minute ago, that's really, really similar to a p-series. So what p-series would 1 over n plus 1 be similar to? 1 over n, right. And basically, the idea is to just kind of get rid of all the extra fluff that's in that series, like all the extra constants and extraneous exponents or just any kind of extra fluff, and just get it down to a simple p-series. So what we're going to do is we're going to compare it to, and you need to write what you're going to compare it to, 1 over n. And what do we know about 1 over n? Does it converge or diverge? It diverges. Why? It is a p-series, and there's a special name. It's a p-series where p equals 1. It's the harmonic, right? And if you just name it the harmonic, then that's good enough justification because it's widely known that the harmonic series diverges. All right, so what our test tells us to do is to take the limit as n approaches infinity of the original series, which is 1 over n plus 1, over the comparison series, which is 1 over n. And when you take two fractions and divide them, what's another way? How do I deal with that?
Flip the second one.
Right. Flip the second one and multiply. So 1 over n plus 1 times n. And what is that limit? Good. So the ratio of the degree of the top and the bottom are the same, so the ratio of leading coefficients is 1. Is 1 a positive finite number? Yes. So therefore, both of these series converge or both diverge, but we know that 1 over n diverges, so therefore the original one also diverges. So that original series diverges by the limit comparison test. And you're more than welcome to write LCT for limit comparison test. And most people would probably agree with me that working that way is probably easier than using the integral test where you're going to have to evaluate that improper integral. It would have been a good idea to actually have checked the nth term test first and take the limit as n approaches infinity of 1 over n plus 1. But that would be 0, and that means it's inconclusive. Yeah. Remember that if the nth term test equals 0, it really means nothing. All right, so this next section, I just want to look at some more complicated series and figure out what we would use, what we would compare it to. So if you were to completely strip down this first series and make it into a p-series, what's the simplest p-series that you think we could deal with? Right. It's 1 over n squared. You take away all the coefficients and anything other than the highest exponent. Does 1 over n squared converge or diverge? It converges. It's a convergent p-series.
How do you know which one's a sub n and which one's b?
A sub, for the comparison test, it doesn't really matter which one you let be a sub n and b sub n. I always let a sub n be my original one. and then B sub n is the comparison one. All right, what do you want to compare 1 over the cubed root of 3n minus 2 to? 1 over the square root of n, or 1 over n to the 1/2. Does that converge or diverge? Good, that one diverges. Okay, next one. Good, 1 over n cubed. And I can tell that y'all are just kind of starting to go with your gut instinct, and that's kind of what you need to do. If you look at the highest exponent on both the top and the bottom, if you reduce that, it becomes 1 over n cubed. And that one also converges. All right, and the last one's a little bit different. I actually can't turn that one into a p-series, but what's the other very simple type of series? Geometric. Can I turn it? Well, first off, is that geometric? No, that 1 plus, if it was just 1 over 5 to the n, that would be geometric because that's the same thing as 1/5 to the n. But that 1 plus throws out the whole geometric thing. So therefore, if I compare it to 1 over 5 to the n or 1/5 to the n power, sometimes it's beneficial to view it as 1/5 to the n, and sometimes it's beneficial to kind of think of it as 1 over 5 to the n. So I kind of write both of them down. That's a geometric series. Does it converge or diverge? It converges. So it's a convergent geometric. All right, to determine the convergence or the divergence of each series. So are we going to compare this one to a geometric or a p-series? P-series, good. Which p-series? One over n to the what? 3/2, right. So you basically have n to the 1/2 on top and n squared on the bottom, so that will reduce to 1 over n to the 3/2. Converge or diverge? All right, so I will take the limit as n approaches infinity of my original series divided by the comparison series. And when you flip the bottom and multiply, you end up with n squared on top and n squared plus 1 on the bottom. So that limit equals 1. Is that a positive finite number? Yes. So therefore, my original one converges since the comparison one converged. They will either both converge or both diverge, as long as that limit is a positive finite number. All right, on number 4. This is probably as difficult as it gets to determine what to compare this to. And this one's kind of interesting because we've got both an exponential part of this, that 2 to the n power is considered an exponential expression, and then we have a polynomial part. And the n over 4n cubed plus 1 is all kind of part of that polynomial part. If the 2 to the n was not there, what would we compare it to? The p-series 1 over n squared, right, that n on top and the n cubed on the bottom. All right, but that 2 to the n is definitely going to affect your terms. So what we're going to do on this one is we're actually going to compare it to 2 to the n divided by n squared. And the big question is, does that converge or diverge? And sometimes some of this just kind of comes down to a gut instinct. Okay. All right, it's going to diverge because the top is growing way faster than the bottom. That's a perfect way to think about it. All right, think about plugging in some numbers for n. If you plug in, say, a 3 for n, what are you going to get on the top? 2 to the third, 8. And the bottom, 3 squared is 9. Well, right now the bottom's bigger. But let's plug in 4. 2 to the 4th is 16, and 4 squared is 16. Now they're the same. Okay, 5. You're going to get 32 on top and 25 on the bottom. If you plug in a 6, you're going to get 64 over 36. And then you're going to get 128 over 49. So do you see how that top is getting bigger much, much faster than the bottom is getting bigger? And it doesn't matter what happened in those small numbers around n equals 1, 2, 3, 4. What matters is way, 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 way out there. So therefore, this comparison series diverges by the nth term test. Because if you were to take the limit as n approaches infinity of 2 to the n over n squared, because the top is getting bigger faster than the bottom, that limit equals infinity. So since that limit doesn't equal 0, the series diverges. An exponential function, which is 2 to the n, will always, always, always outgrow a polynomial function. So even if you had 2 to the n over n to the 5,000th power, I mean, n to the 5,000th, when you plug numbers in, that's going to get pretty big, but eventually 2 to the n is going to get even bigger. So an exponential will always outgrow a polynomial. So from here on out, you can just kind of look at this limit right here and say, oh, well, that's going to be infinity. What if I had the polynomial on top and the exponential on the bottom? What would that limit be? 0. Yeah. The limit would be 0. Okay, so I know, and we're kind of focused just on that, the comparison right now, so don't lose sight of the whole problem. So the whole problem is that I need to take the limit as n approaches infinity of my original one. And instead of dividing by my comparison series, I'm going to go ahead and flip and multiply by it. So n squared over 2 to the n. What's that limit? It's 1/4, right? Your 2 to the n's will cancel. The degrees on top and bottom match. Ratio of leading coefficients is 1/4, which is a positive finite number, so therefore they both diverge. It diverges by the limit comparison test. And really, that's way more complicated than you're probably going to see on the AP exam. It's probably going to be something more like number 3 or even number 1. Let's just try the nth term test. Maybe it'll be a shot in the dark and we'll get lucky. As n approaches infinity, what's the top is oscillating between what? -1 and 1. The bottom is getting bigger and bigger and bigger. So the limit is actually 0, even though your limit is 0, but you're approaching 0 kind of from the positive and negative sides. Either way, the nth term test doesn't work. So I am going to have to use a comparison test. I'm going to just go ahead and compare it to 1 over n squared. And the reason that I don't really need to consider that sign n is because the sign of n is only going to fall between -1 and 1. And therefore, that's not really going to make my terms significantly bigger or smaller as n increases. So 1 over n squared converges. It's a convergent p-series. So the limit as n approaches infinity of sine n over n squared plus 1 divided by 1 over n squared would be times n squared. What do you think that limit is? Okay, the n squared over n squared we've got the same degree, so the leading coefficients is kind of 1. However, what is sine n doing to 1?
The limit does not exist.
Right, that limit does not exist because that sine n is making it, because the degree was the same on top and bottom, sine n is making it just oscillate back and forth, whereas when I was just taking the limit of the original series, it was oscillating back and forth between 0. Okay, so in order for the limit comparison test to work, I need to be able to find that limit. So this is kind of a downfall of the limit comparison test. So that brings up another comparison test called the direct comparison test.